The Higgs Boson, discovered at the Large Hadron Collider on July 4, 2012, revealed one of the universe's most profound secrets. Mass isn't a fundamental property of particles. It is something they acquire by interacting with an invisible field that fills every cubic centimeter of space throughout the entire universe. This field, called the Higgs field, is so fundamental that without it, electrons would be massless atoms, couldn't form, stars wouldn't shine, and the universe would be nothing but a cold soup of massless particles racing through space at the speed of light. Here is what makes this discovery so mind-bending: the mathematics that describe the fundamental forces of nature, the equations that govern electromagnetism, the weak nuclear force and the strong nuclear force, only work if particles have no mass whatsoever. Yet obviously, particles do have mass. This created what physicists call the mass problem, a contradiction so fundamental it threatened to make our entire understanding of particle physics mathematically inconsistent. Tonight we're going to explore the most important discovery in physics of the 21st century, understand how a single invisible field solves one of nature's deepest puzzles, and discover what the Higgs mechanism reveals about the hidden architecture of reality itself. Dr. Peter Higgs, the theoretical physicist who first proposed this mechanism in 1964, spent nearly 50 years waiting for experimental confirmation of his revolutionary idea. When the discovery was finally announced by CERN scientists on that historic July morning, Higgs himself was moved to tears. He had witnessed the confirmation of something so fundamental that it explains why the universe has structure, why chemistry is possible, and why life itself can exist. The Higgs field isn't just another scientific discovery. It is the revelation of a hidden layer of reality that underlies everything we see and touch. Imagine if you discovered that the air around you wasn't empty space, but actually a thick, invisible medium that gave weight to everything passing through it. That's exactly what the Higgs field represents. Except this medium isn't air, it's a quantum field more fundamental than space and time themselves. Consider this staggering fact. The Higgs field has been active throughout the entire 13.8 billion year history of the universe. Every star that ever formed, every planet that ever coalesced from cosmic dust, every living creature that ever evolved, all of these exist only because the Higgs field continuously provides mass to the fundamental particles from which everything is built. Without this field, the universe would be a formless void populated only by massless particles that could never slow down, never stick together, never form the complex structures we call atoms, molecules, and life. The discovery required the most expensive and complex scientific instrument ever built by humanity: the Large Hadron Collider, a 27-kilometer underground ring where protons smash together at 99.9999991% the speed of light. These collisions recreate conditions that existed just after the Big Bang, when the Higgs field first switched on and began giving mass to particles for the very first time in cosmic history. What makes the Higgs boson so elusive is that it's not really a particle in the traditional sense. It's more like a ripple in the invisible field that fills all of space. Detecting this ripple required generating collision energies equivalent to the temperatures that existed when the universe was just 1/trillionth of a second old. At those energies, the hidden quantum fields that normally remain invisible suddenly become detectable through the exotic particles they produce. The mathematical framework describing the Higgs mechanism connects to some of the deepest concepts in modern physics: spontaneous symmetry breaking, gauge field theory, and the relationship between mass and energy described by Einstein's E=mc. But perhaps most remarkably, the Higgs field represents the first time in history that humanity has discovered a fundamental field that exists everywhere in the universe yet remained completely hidden until we developed the theoretical and experimental tools to detect it. Here is what makes this discovery philosophically profound. The Higgs field reveals that what we call empty space is actually filled with invisible quantum fields that determine the fundamental properties of matter. Space isn't empty, it's alive with quantum activity that shapes the very nature of existence. The Higgs field shows us that reality has hidden layers we're only beginning to understand. The implications extend far beyond particle physics. The Higgs mechanism might explain how the universe transitioned from the formless energy, soup of the early Big Bang, to the structured cosmos we inhabit today. It provides insights into why the fundamental forces have the strengths they do, why particles have the specific masses we observe, and potentially how our universe might relate to parallel universes where the Higgs field has different properties. As we explore the 11 profound aspects of the Higgs boson and the mass-giving mechanism it represents, we'll discover how this invisible field solved one of physics' greatest mysteries, learn why finding it required recreating the conditions of the early universe, and understand what this discovery reveals about the deepest layers of reality that exist beyond our direct perception. If you're fascinated by discoveries that reveal the hidden mechanisms underlying existence itself, subscribe and hit thumbs up. And here is a question that will transform how you think about reality. If the most fundamental property we experience, the weight and solidity of matter, comes from interaction with an invisible field, we can directly perceive what other hidden layers of reality might exist right here, right now, shaping our existence in ways we haven't yet discovered. Comment below with your thoughts. I'll pin the most mind-expanding answer. The Higgs boson represents more than just a scientific milestone. It is humanity's first glimpse into the quantum scaffolding that holds reality together, the invisible infrastructure that makes existence itself possible. In understanding how this single field gives mass to everything in the universe, we begin to appreciate that the familiar world of solid objects and predictable physics emerges from quantum foundations far stranger and more wonderful than we ever imagined. Now, let's begin our journey into the discovery that reveals why anything exists at all and how an invisible field permeating all of space solved one of the deepest mysteries in the history of human knowledge. Chapter 1. Mass Mystery. The mystery that led to the discovery of the Higgs boson begins with a simple question that haunted physicists for decades. Why do particles have mass? This question seems almost trivial, like asking why rocks fall down instead of up, until you realize that according to the fundamental equations of particle physics, particles shouldn't have any mass at all. This contradiction between mathematical theory and physical reality created one of the deepest puzzles in the history of science. To understand this mystery, we need to examine how mass behaves at the most fundamental level of reality. When we think about mass in everyday life, we imagine it as an inherent property of matter, something that simply belongs to objects, the way color belongs to a red apple or hardness belongs to a diamond. But as physicists probed deeper into the structure of matter, they discovered that mass is far more mysterious than our everyday experience suggests. The first hint that mass might not be fundamental came from Einstein's special theory of relativity in 1905. Einstein's famous equation, E=mc, revealed that mass and energy are interchangeable. Mass is simply another form of energy. This insight suggested that mass might not be a basic property of matter, but rather something that emerges from more fundamental processes involving energy and motion. However, Einstein's work didn't explain where mass comes from or why different particles have the specific masses they do. The mystery deepened dramatically with the development of quantum field theory in the 1940s and 1950s. This mathematical framework describes all fundamental particles as excitations in underlying quantum fields that fill all of space. The electron, for example, is an excitation in the electron field, while photons are excitations in the electromagnetic field. These quantum field equations are extraordinarily successful at describing how particles interact and behave, but they only work mathematically if the fundamental particles have zero mass. Dr. Yang Chen-Ming and Robert Mills developed the mathematical foundation for understanding fundamental forces through what became known as Yang-Mills gauge theory. Their equations elegantly describe how particles interact through force-carrying particles called gauge bosons. But there is a catch. The mathematical consistency of these gauge theories requires all particles to be massless. Any attempt to simply add mass terms to the equations destroys their fundamental symmetries and makes the mathematics inconsistent. This created what physicists call the gauge theory mass problem. On one hand, we had beautifully consistent mathematical theories that explained fundamental forces, but only worked for massless particles. On the other hand, we had experimental reality where particles obviously do have mass. The two seemed irreconcilably incompatible, suggesting either that our theoretical understanding was fundamentally flawed or that mass emerges through some hidden mechanism we hadn't yet discovered. Professor Steven Weinberg from the University of Texas, who later won the Nobel Prize for his work on the unified electroweak theory, described this puzzle as the most important problem in particle physics. The contradiction wasn't just academic, it threatened to undermine the entire theoretical framework that physicists had spent decades developing to understand the fundamental forces of nature. The mass problem became even more acute when physicists realized that electromagnetic and weak nuclear forces could be unified into a single electroweak force, but only if the particles mediating these forces were massless. Yet experimental evidence clearly showed that the W and Z bosons, which carry the weak force, have substantial masses about 80 and 91 times the mass of a proton, respectively. How could forces be unified through massless gauge theories when their mediating particles clearly possessed mass? Dr. Sheldon Glashow from Harvard University made crucial progress by showing how electromagnetic and weak forces could indeed be unified mathematically, but his theory faced the same mass problem. The unification worked perfectly in the mathematical realm of massless particles, but seemed impossible to reconcile with the massive particles observed in experiments. The theory predicted that the W and Z bosons should be massless, directly contradicting experimental measurements. This contradiction forced physicists to consider radical possibilities. Perhaps mass wasn't a fundamental property at all, but rather an acquired characteristic that particles gain through interaction with something that fills all of space but remains invisible to direct observation. This something would need to selectively give different masses to different types of particles while preserving the underlying mathematical symmetries required by gauge theories. The concept seemed almost mystical, an invisible presence throughout the universe that determines one of the most basic properties we experience, the weight and inertia of matter itself. Yet without such a mechanism, physicists faced an impossible choice between mathematical consistency and experimental reality. The equations of particle physics simply could not accommodate both the unified description of forces and the observed masses of particles. Professor Gerard 't Hooft from Utrecht University made another crucial contribution by proving that gauge theories could be renormalizable, mathematically consistent at all energy scales, but only under very specific conditions. His work showed that theories like the Standard Model could indeed provide finite, meaningful predictions, but the renormalization procedure required careful treatment of particle masses that seemed to point toward some hidden mass generation mechanism. The experimental evidence for particle masses came from increasingly sophisticated accelerator experiments throughout the 1950s and 1960s. At laboratories like CERN in Europe and Fermilab in the United States, physicists smashed particles together at ever higher energies, precisely measuring the masses of fundamental particles. These experiments revealed a puzzling pattern. Particles seemed to fall into families with specific mass relationships, but there was no obvious underlying principle explaining why particles had the particular masses they possessed. Dr. Murray Gell-Mann's discovery of the quark model in 1964 added another layer to the mass mystery. Gell-Mann showed that protons and neutrons are composed of smaller particles called quarks, bound together by this strong force. But the masses of individual quarks didn't add up to the masses of the composite particles they formed. Most of a proton's mass, it turned out, comes from the binding energy that holds quarks together rather than from the quarks themselves, another indication that mass has hidden, emergent properties. The mystery became even more complex when physicists realized that some particles, like neutrinos, appeared to be massless or nearly massless, while others, like the W and Z bosons, were extremely massive. There seemed to be no fundamental principle governing which particles acquire mass and which remain massless. The pattern appeared almost arbitrary, as if mass was assigned to particles by some external agency rather than emerging from their intrinsic properties. Professor David Gross from Princeton University, who later won the Nobel Prize for discovering asymptotic freedom in the strong force, described the mass problem as the missing piece of the puzzle. He and other leading physicists recognized that solving the mass mystery would require a conceptual breakthrough as fundamental as quantum mechanics itself, a new understanding of how the universe operates at its deepest level. The search for this missing piece led physicists to explore increasingly exotic theoretical possibilities. Perhaps particles acquire mass by interacting with the quantum vacuum itself, the seething sea of virtual particles that quantum mechanics predicts should fill even empty space. Maybe mass emerges from hidden extra dimensions that we can't directly perceive. Or possibly, the universe contains invisible fields that selectively couple to different particles, endowing them with the masses we observe. Each of these possibilities required theoretical frameworks that extended far beyond the established physics of the time. Physicists found themselves in the unusual position of knowing that something fundamental was missing from their understanding, but having no clear experimental guidance about what that something might be. The mass mystery seemed to require a leap of theoretical imagination comparable to Einstein's insights about space and time. The urgency of solving this puzzle intensified as physicists developed increasingly ambitious theories attempting to unify all fundamental forces. These grand unified theories promised to reveal deep connections between seemingly different aspects of nature, but they all foundered on the mass problem. Without understanding how particles acquire mass, it seemed impossible to achieve the theoretical unification that many physicists saw as the ultimate goal of fundamental research. The stage was set for one of the most important theoretical breakthroughs in the history of physics, a kaisis revelation that would show how an invisible field permeating all of space could solve the mass mystery while preserving the mathematical elegance of gauge theories. This breakthrough would not only explain why particles have mass, but would reveal a hidden layer of reality that shapes every aspect of the physical world we experience. Chapter 2: Hidden Fields. The solution to the mass mystery required physicists to fundamentally reimagine the nature of empty space itself. In our everyday experience, empty space appears to be truly empty, a void where nothing exists except the occasional passage of light or matter. But quantum mechanics reveals that what we call empty space is actually filled with invisible quantum fields that constantly fluctuate with tremendous energy and activity. These fields are so fundamental that they exist everywhere throughout the universe, yet they remain completely invisible to our direct perception. The concept of quantum fields emerged from the marriage of quantum mechanics and special relativity in the 1940s. Physicists like Paul Dirac and Richard Feynman developed mathematical frameworks showing that every type of particle in the universe corresponds to an underlying quantum field. The electron is an excitation in the electron field. Photons are excitations in the electromagnetic field, and quarks are excitations in various quark fields. These fields exist everywhere in space, even in regions where no particles are present. Dr. Julian Schwinger from Harvard University made crucial theoretical advances showing how these quantum fields constantly fluctuate due to Heisenberg's uncertainty principle. Even in the complete absence of matter and energy, these fields undergo quantum fluctuations that briefly create virtual particles and antiparticles that immediately annihilate each other. The vacuum of space is thus alive with quantum activity, a dynamic medium that influences how particles behave and interact. But the breakthrough insight that would solve the mass mystery came from considering a special type of quantum field with unusual properties. Most quantum fields, like the electromagnetic field, have their minimum energy state when the field value is zero everywhere. This makes intuitive sense. When no photons are present, the electromagnetic field should be turned off. However, quantum field theory allows for the possibility of fields whose minimum energy state occurs when the field has a non-zero value everywhere in space. Professor Jeffrey Goldstone from MIT investigated the mathematical consequences of such fields and discovered something remarkable. When a quantum field has a non-zero value in its ground state, it can endow other particles with mass through their interactions with this background field. The mechanism works like this. Particles that interact strongly with the background field experience more resistance to acceleration and thus behave as if they have more mass, while particles that interact weakly with the field acquire less mass. This concept seemed almost magical, an invisible field filling all of space that could selectively give different masses to different particles depending on how strongly they coupled to the field. But the mathematical formalism was precisely what was needed to solve the gauge theory mass problem. Particles could start out massless in the fundamental equations, but acquire mass through interaction with this background field without breaking the underlying symmetries that made the theories mathematically consistent. The theoretical framework describing this mass generation mechanism required understanding spontaneous symmetry breaking, a phenomenon where the underlying laws of physics possess certain symmetries, but the actual state of the system appears to break those symmetries. Dr. Yoichiro Nambu from the University of Chicago pioneered the application of spontaneous symmetry breaking to particle physics, showing how it could resolve the tension between symmetric theories and asymmetric observations. The classic analogy for spontaneous symmetry breaking involves a ball balanced at the top of a hill. The laws of physics, represented by the shape of the hill, might be perfectly symmetric with respect to which direction the ball could roll. But once the ball actually rolls down, it breaks this symmetry by choosing a particular direction. Similarly, the fundamental laws might be symmetric with respect to particle masses, but the actual state of the universe breaks this symmetry by filling space with a field that gives particles specific masses. Professor Abdus Salam from Imperial College London made important contributions to understanding how spontaneous symmetry breaking could be implemented in gauge theories. He showed that when a field spontaneously acquires a non-zero value throughout space, it doesn't destroy the underlying gauge symmetry, but rather hides it in such a way that particles can acquire mass while the theory remains mathematically consistent. This hidden symmetry becomes evident only at extremely high energies, where the symmetry-breaking effects become less important. The mathematics of hidden fields revealed something profound about the structure of reality. What we experience as fundamental properties of particles, their masses, actually emerge from interactions with invisible fields that permeate all of space. This suggested that many other fundamental properties might also be emergent rather than intrinsic, arising from interactions with hidden aspects of reality that we haven't yet learned to detect. Dr. Steven Weinberg's unified electroweak theory provided the first successful application of hidden field mass generation to real physics. Weinberg showed how electromagnetic and weak forces could be unified into a single force, with the differences between them arising from spontaneous symmetry breaking caused by a hidden field. In the early universe, when temperatures were extremely high, electromagnetic and weak forces would have been indistinguishable. But as the universe cooled, the hidden field acquired its current value, breaking the symmetry and giving the W and Z bosons their large masses while leaving the photon massless. The experimental implications of hidden fields were profound. If particles acquire mass through interaction with invisible background fields, then it should be possible, at least in principle, to detect these fields directly by creating conditions where they become disturbed from their ground state. This would require enormous energies comparable to those that existed in the early universe when the fields first acquired their current values. Professor Martinus Veltman from Utrecht University, working with his student Gerard Tuhuf, proved that gauge theories with spontaneous symmetry breaking are indeed mathematically consistent and renormalizable. Their work showed that theories incorporating hidden mass-generating fields could make finite, meaningful predictions that could be tested experimentally. This mathematical proof was crucial for establishing that hidden field theories weren't just elegant speculation, but represented potentially correct descriptions of nature. The concept of hidden fields filling all of space challenged fundamental assumptions about the nature of emptiness and existence. If space is filled with invisible fields that determine basic properties of matter, then our everyday notion of empty space is completely wrong. Space isn't empty. It is a dynamic medium filled with quantum fields that actively shape the behavior of everything within it. We live immersed in invisible fields that are as fundamental to our existence as the air we breathe. Theoretical calculations revealed that these hidden fields must possess enormous energy densities. The energy stored in quantum field fluctuations throughout space is predicted to be many orders of magnitude larger than the energy contained in all the matter and radiation in the observable universe. This creates what physicists call the cosmological constant problem. If hidden fields have such enormous energy densities, they should gravitationally affect the expansion of the universe in ways that aren't observed. Dr. Edward Witten from the Institute for Advanced Study explored how hidden fields might be connected to other mysterious aspects of physics, including dark matter and dark energy. He showed that certain theoretical models predict the existence of multiple hidden fields with different properties, some of which might be responsible for phenomena we observe but don't yet understand. The hidden field responsible for giving particles mass might be just one member of a larger family of invisible fields that shape cosmic evolution. The search for hidden fields also raised profound questions about the relationship between mathematics and physical reality. These fields were initially postulated purely on mathematical grounds. They were required to make gauge theories mathematically consistent. Yet they predicted the existence of invisible aspects of reality that should, in principle, be experimentally detectable. This suggested a deep connection between mathematical beauty and physical truth that continues to guide theoretical physics today. Modern quantum field theory describes the universe as filled with dozens of different quantum fields, each corresponding to a different type of particle or force. But among all these fields, the hidden field responsible for mass generation holds a special place. It's the only field we know of that has a non-zero value everywhere in space, making it unique among the fundamental fields of nature. This uniqueness suggests that the mass-generating field might hold clues to even deeper principles governing the structure of reality. The theoretical framework of hidden fields also suggested new possibilities for understanding consciousness, information, and the relationship between mind and matter. If physical reality emerges from interactions with invisible fields that determine fundamental properties like mass, then perhaps other aspects of existence, including consciousness itself, might also emerge from interactions with hidden fields that science has yet to discover. As physicists developed increasingly sophisticated mathematical tools for describing hidden fields, they realized that detecting these fields would require experiments of unprecedented scale and precision. The hidden field responsible for mass would remain invisible until technology advanced enough to probe the quantum vacuum itself. revealing the dynamic invisible medium that shapes every aspect of our physical existence. Chapter 3. Theoretical Revolution. The theoretical breakthrough that would eventually lead to the discovery of the Higgs boson emerged from the brilliant minds of 6 physicists working independently in the mid-1960s. These scientists, Peter Higgs, Francois Englert, Robert Brout, Gerald Guralnick, C.R. Hagen, and Tom Kibble developed mathematical frameworks showing exactly how an invisible field could give mass to particles while preserving the elegant symmetries required by gauge theories. Their work represented one of the most profound theoretical revolutions in the history of physics. The revolution began with Peter Higgs at the University of Edinburgh, who was investigating the mathematical structure of gauge theories and spontaneous symmetry breaking. In the summer of 1964, Higgs was working through the implications of a field that could acquire a DAM, non-zero value throughout space when he realized something extraordinary. Such a field wouldn't just give mass to other particles through their interactions with it. The field itself would have a detectable particle-like excitation that could in principle be observed experimentally. Higgs's insight was that when any quantum field is disturbed from its equilibrium state, the disturbance propagates through space as a particle. For most fields, like the electromagnetic field, these excitations are the familiar particles we know, photons, in the case of electromagnetic disturbances. But for a field that has non-zero value everywhere in space, the particle-like excitation would have unique properties that would make it both incredibly difficult to detect and absolutely crucial for understanding the fundamental nature of mass. This particle, which came to be known as the Higgs boson, would be the smoking gun for the existence of the invisible field. If the mass-generating field really existed throughout space, then high-energy experiments should be able to create temporary disturbances in this field that would briefly manifest as detectable particles before quickly decaying into other particles. The challenge would be building experiments powerful enough to create such disturbances and sensitive enough to detect their fleeting signatures. Dr. Francois Englert and Robert Brout at the Université Libre de Bruxelles was simultaneously developing their own version of the mechanism. Their approach emphasized the mathematical elegance of spontaneous symmetry breaking in gauge theories, showing how the mechanism could solve fundamental problems in particle physics while making specific, testable predictions. The Englert-Brout mechanism demonstrated that the theoretical framework wasn't just mathematically beautiful, it was scientifically robust. The work of Gerald Guralnick, C.R. Hagen, and Tom Kibble at Imperial College London provided additional mathematical rigor and explored the broader implications of the mechanism. Their detailed calculations showed how the mass-generating field would affect not just individual particles but entire families of particles, explaining patterns in particle masses that had previously seemed arbitrary. The Guralnick-Hagen-Kibble formulation revealed that the mechanism could account for the masses of all fundamental particles in a unified theoretical framework. Professor Stephen Weinberg recognized the revolutionary implications of these theoretical developments and incorporated them into his unified theory of electromagnetic and weak forces. Weinberg, his 1967 paper, A Model of Leptons, showed how the Higgs mechanism could explain why photons are massless while W and Z bosons are massive, solving one of the most puzzling aspects of fundamental force unification. His work demonstrated that the theoretical revolution wasn't just academic, it could explain real experimental observations. The mathematical framework describing the Higgs mechanism revealed profound connections between seemingly unrelated aspects of physics. The same mathematics that explain particle masses also predicted the existence of specific relationships between fundamental forces, suggested new conservation laws, and provided insights into the evolution of the universe from its earliest moments. The theory implied that understanding mass was the key to understanding much deeper aspects of reality. Dr. Abdus Salam independently developed similar ideas, showing how spontaneous symmetry breaking could unify electromagnetic and weak forces while explaining particle masses. Salam's work emphasized the aesthetic beauty of the unified theory, the way it revealed hidden connections between phenomena that appeared completely different on the surface. For Salam, the theoretical revolution represented not just scientific progress, but a glimpse into the fundamental harmony underlying nature. The theoretical predictions were remarkably specific. The Higgs mechanism didn't just predict that particles should have mass, it predicted exactly how different particles should acquire different masses based on their coupling strengths to the Higgs field. The theory predicted that the top quark should be much heavier than other quarks, that neutrinos should be much lighter than electrons, and that the W and Z bosons should have precisely determined mass ratios. Perhaps most remarkably, the theory predicted its own experimental signature. The Higgs boson should decay in specific ways, producing characteristic patterns of particles that could be detected in high-energy experiments. The theory provided a detailed roadmap for how to search for the particle, what signatures to look for, and what backgrounds to exclude. It was a theorist's dream, a mathematical framework that made precise, testable predictions about phenomena at the frontiers of experimental capability. Professor John Ellis from CERN became one of the leading advocates for experimental searches for the Higgs boson, translating the abstract theoretical predictions into concrete experimental programs. Ellis's work showed how the theoretical revolution could guide the design of particle accelerators and detectors capable of probing the deepest levels of reality. The theory provided not just predictions, but a research program that could occupy experimentalists for decades. The theoretical framework also suggested profound connections to cosmology and the early universe. If the Higgs field gives mass to particles today, then there must have been a phase transition in the early universe when this field first acquired its non-zero value. Before this transition, all particles would have been massless, and the universe would have been a very different place. The theoretical revolution thus provided insights into cosmic evolution and the conditions that made the formation of atoms, molecules, and complex structures possible. Dr. Michael Duff from Imperial College London explored how the Higgs mechanism might be connected to other theoretical developments in physics, including string theory and theories of extra dimensions. Duff's work suggested that the mass-generating field might be just one manifestation of more fundamental structures that exist in higher dimensional spaces we can't directly perceive. The theoretical revolution might represent humanity's first glimpse of these deeper layers of reality. The mathematics of the Higgs mechanism also revealed unexpected connections to condensed matter physics and the behavior of materials at very low temperatures. Physicists like Philip Anderson from Princeton University showed that similar symmetry-breaking mechanisms occur in superconductors, where electrons form Cooper pairs that can flow without resistance. The theoretical revolution thus unified aspects of particle physics and material science in ways that hadn't been anticipated. The theoretical predictions faced initial skepticism from some physicists who questioned whether such an exotic mechanism could really be responsible for something as fundamental as mass. Professor Murray Gell-Mann, the discoverer of quarks, initially referred to the Higgs mechanism as that toilet paper theory because of the numerous pages of mathematical calculations required to understand it. However, as the theoretical framework proved successful in explaining more and more experimental observations, skepticism gradually gave way to acceptance. The revolution wasn't just theoretical, it required the development of entirely new mathematical techniques for handling gauge theories with spontaneous symmetry breaking. Physicists developed sophisticated methods for calculating quantum corrections, understanding symmetry breaking phase transitions, and predicting the properties of particles that hadn't yet been discovered. These mathematical tools would prove essential not just for understanding the Higgs mechanism, but for advancing theoretical physics more generally. The theoretical framework also made troubling predictions about the ultimate fate of the universe. If the Higgs field could undergo phase transitions, changing its value throughout space, then our current vacuum state might not be stable. The universe might eventually tunnel to a different vacuum state where particles have different masses or where the laws of physics operate differently. This possibility, known as vacuum decay, represents one of the most exotic predictions of the theoretical revolution. As the theoretical revolution matured through the 1970s and 1980s, it became clear that finding the Higgs boson experimentally would require technological capabilities that pushed beyond the limits of existing particle accelerators. The energy scales needed to create and detect Higgs particles would require machines orders of magnitude more powerful than anything that existed. The theoretical revolution thus posed a grand challenge to experimental physics. Build machines capable of probing the quantum vacuum itself and revealing the hidden fields that shape all of reality. Chapter 4. Quantum Vacuum. The most mind-bending aspect of the Higgs mechanism is that it reveals the quantum vacuum, what we naively call empty space, to be anything but empty. Instead, the vacuum is a dynamic, seething medium filled with quantum fields that constantly fluctuate and interact with tremendous energy and complexity. Understanding the quantum vacuum is crucial for grasping how the Higgs field can exist everywhere in space while remaining invisible, and why disturbing this hidden medium requires the most powerful particle accelerators ever built. Quantum mechanics fundamentally changed our understanding of empty space through Heisenberg's uncertainty principle, which states that energy and time cannot be simultaneously determined with perfect precision. This seemingly abstract mathematical constraint has profound physical consequences. It means that even in regions completely devoid of matter and radiation, quantum fields must constantly fluctuate, briefly creating virtual particles and antiparticles that immediately annihilate each other. Dr. Hendrik Casimir predicted in 1948 that these quantum vacuum fluctuations would produce measurable physical effects. The Casimir effect, which involves attractive forces between closely spaced metal plates due to quantum vacuum fluctuations, was experimentally confirmed and provided the first direct evidence that empty space contains real physical energy. The quantum vacuum isn't a philosophical abstraction, it's a tangible aspect of reality with observable consequences. The energy density of quantum vacuum fluctuations is staggering beyond imagination. Theoretical calculations suggest that every cubic centimeter of space contains quantum field energy equivalent to all the energy in all the stars in the observable universe. This prediction creates what physicists call the cosmological constant problem. If the vacuum really contains this much energy, its gravitational effects should dominate the expansion of the universe in ways that clearly aren't observed. Professor Steven Weinberg from the University of Texas has spent decades working on the cosmological constant problem, exploring whether the enormous vacuum energy somehow cancels out through unknown symmetries or whether our understanding of quantum field theory in curved spacetime is fundamentally incomplete. The problem remains one of the deepest unsolved mysteries in physics, suggesting that our understanding of the quantum vacuum remains profoundly incomplete. Within this turbulent sea of quantum fluctuations, the Higgs field occupies a unique position. Unlike other quantum fields, which have their minimum energy state when their field value is zero everywhere, the Higgs field has its lowest energy configuration when it has a specific non-zero value throughout all of space. This means that what we call the vacuum state of the universe actually corresponds to a condition where the Higgs field is turned on everywhere. The mechanism by which the Higgs field acquired its non-zero vacuum value represents one of the most important phase transitions in cosmic history. In the extremely high temperature conditions of the early universe, just after the Big Bang, thermal energy was so intense that the Higgs field couldn't settle into its minimum energy state. Instead, it fluctuated wildly around zero, and all particles were effectively massless, traveling at the speed of light. Dr. Alan Guth from MIT has explored how cosmic inflation, the rapid exponential expansion of space during the universe as first fraction of a second might have influenced the Higgs field as transition to its current state. Guth's work suggests that inflationary expansion could have played a crucial role in ensuring that the Higgs field acquired the same non-zero value throughout the entire visible universe, explaining why particles have consistent masses across cosmic distances. As the universe expanded and cooled, it eventually reached a critical temperature where the Higgs field underwent spontaneous symmetry breaking, suddenly acquiring its non-zero value throughout space. This phase transition, which occurred when the universe was roughly 1 picosecond old, fundamentally changed the nature of reality. Before this transition, particles were massless and the universe was a formless soup of radiation. After the transition, particles acquired mass, making possible the formation of atoms, molecules, and all complex structures. The quantum vacuum's role in mass generation works through a mechanism that seems almost mystical, but follows precise mathematical laws. Particles acquire mass by constantly interacting with the Higgs field as they move through space. A particle with strong coupling to the Higgs field experiences more resistance to acceleration, and thus behaves as if it has more mass, while particles with weak coupling experience less resistance and appear lighter. Professor Frank Wilczek from MIT has described this process as particles swimming through cosmic molasses. The Higgs field acts like an invisible medium that selectively impedes different types of particles to different degrees. But unlike ordinary molasses, which slows down particles through friction, the Higgs field affects particles through quantum mechanical interactions that preserve energy and momentum while changing the particle's inertial properties. The vacuum expectation value of the Higgs field, the strength of the field in empty space, is approximately 246 GeV, billion electron volts, in the units physicists use to measure energy and mass. This might seem like an arbitrary number, but it's actually one of the most important constants in nature. This single number determines the masses of all fundamental particles and sets the energy scale for electroweak interactions. Quantum field theory predicts that the Higgs vacuum expectation value should fluctuate due to quantum corrections involving virtual particles. These fluctuations are incredibly tiny, far smaller than could be detected by any conceivable experiment, but their theoretical implications are profound. They suggest that the apparent stability of particle masses emerges from an underlying quantum mechanical balancing act that could, in principle, be disturbed by sufficiently extreme conditions. Dr. Juan Maldacena from the Institute for Advanced Study has investigated how quantum vacuum fluctuations might be related to fundamental aspects of spacetime geometry. His work on the AD-SCFT correspondence suggests that quantum field fluctuations in one region of space might be mathematically equivalent to gravitational dynamics in higher dimensional spaces we can't directly observe. The quantum vacuum might thus be our window into hidden dimensions of reality. The search for the Higgs boson required creating conditions where the quantum vacuum itself becomes excited and reveals its hidden structure. Particle accelerators accomplish this by smashing particles together with energies comparable to the Higgs vacuum expectation value, temporarily creating regions where the normal vacuum state is disrupted. In these tiny, fleeting volumes of space, the Higgs field can be knocked away from its equilibrium value, creating particle-like excitations that briefly exist before decaying. The energy required to disturb the Higgs vacuum explains why the Higgs boson took so long to discover. Creating a single Higgs particle requires energies equivalent to about 125 times the mass of a proton, energies that existed naturally only in the first moments after the Big Bang or in the cores of the most extreme cosmic phenomena. Building machines capable of routinely producing such energies required decades of technological development and international cooperation. Professor Lisa Randall from Harvard University has explored how the properties of the quantum vacuum might vary in different regions of a larger multiverse. If our universe is just one of many possible universes with different physical laws, then different regions of the multiverse might have Higgs fields with different vacuum expectation values, leading to universes where particles have entirely different masses and where the possibilities for complex structure formation vary dramatically. The stability of the Higgs vacuum raises profound questions about the ultimate fate of our universe. Quantum field theory suggests that our current vacuum state might not represent the absolute minimum energy configuration. There might exist other vacuum states with lower energy, and quantum tunneling could, in principle, cause the entire universe to spontaneously transition to one of these lower energy states. Such a transition would instantly change the masses of all particles, likely destroying all atoms and complex structures. Theoretical calculations by Dr. Joseph Liken from Fermilab suggest that the measured properties of the Higgs boson place our universe very close to the boundary between vacuum stability and instability. The universe appears to exist in what physicists call a metastable state, stable enough to persist for cosmological timescales, but potentially unstable over much longer periods. This precarious balance might hold clues to deeper principles governing the relationship between quantum fields and spacetime. The quantum vacuum also serves as the medium through which all fundamental forces operate. Electromagnetic interactions, for example, work through the exchange of virtual photons that exist briefly in the quantum vacuum before being absorbed by other particles. The Higgs mechanism shows that even mass, our most familiar property of matter, emerges from interactions with quantum vacuum fluctuations of an invisible field. Recent developments in quantum field theory suggest that the quantum vacuum might possess even richer structure than previously imagined. Theoretical work on vacuum entanglement suggests that quantum mechanical correlations exist between different regions of the vacuum, creating a web of connections that spans cosmic distances. The Higgs field might be just one aspect of this larger quantum network that underlies all of physical reality. As our understanding of the quantum vacuum deepens, it becomes clear that what we call empty space is actually the most fundamental aspect of physical reality, a dynamic medium that shapes every interaction, determines every particle property, and might hold the key to understanding the deepest mysteries of existence itself. Chapter 5. Energy Scales. Understanding why the Higgs boson took nearly 50 years to discover requires grasping the concept of energy scales in particle physics, the idea that different physical phenomena become apparent only when you probe matter with specific amounts of energy. The Higgs boson lives at an energy scale so high that accessing it required building the most powerful particle accelerator in human history and developing detection technologies sensitive enough to identify a single particle among billions of collision events. In particle physics, energy and mass are interchangeable according to Einstein's E equals mc, which means that creating particles with larger masses requires proportionally higher energies. The Higgs boson has a mass of approximately 125 GeV squared, about 133 proton masses, making it one of the heaviest fundamental particles known. This enormous mass explains why the Higgs remained hidden until we developed accelerators capable of reaching the required energy scales. The concept of energy scales in physics is beautifully illustrated by how the same material reveals different properties when examined with different energies. Looking at matter with low-energy visible light reveals molecular and atomic structure. Higher energy X-rays penetrate deeper, revealing the positions of atomic nuclei. Even higher energy gamma rays can probe the internal structure of protons and neutrons, revealing their constituent quarks. The Higgs boson exists at energy scales so extreme that accessing it requires energies comparable to those in the cores of exploding supernova. Dr. Leon Lederman from Fermilab, who coined the popular nickname God particle for the Higgs boson, emphasized that the particle's discovery would require the energy scale of creation itself. Lederman understood that finding the Higgs meant recreating conditions that existed when the universe was less than 1 picosecond-old temperatures of trillions of degrees, where the normal rules of atomic physics completely break down. The Large Hadron Collider at CERN was specifically designed to reach the energy scales needed for Higgs discovery. Professor John Ellis from CERN has calculated that the probability of producing a single Higgs boson in a typical LHC collision is approximately 1 in 10 billion. This incredibly low production rate means that even at the LHC's collision rate of 600 million collisions per second, Higgs particles are created only about once every few seconds. Finding these rare events among the overwhelming background of other collision products required analysis techniques of extraordinary sophistication. The energy scale needed to probe the Higgs mechanism directly relates to the field S vacuum expectation value of 246 GeV. This energy scale, known as the electroweak scale, represents the point where electromagnetic and weak nuclear forces become unified. Below this energy scale, these forces appear different because the Higgs field breaks the symmetry between them. Above this energy scale, the forces become indistinguishable, revealing the underlying unified nature of electroweak interactions. The hierarchy of energy scales in particle physics reveals a cosmic coincidence that makes our existence possible. If the electroweak scale were much higher, the Higgs field would be too strong, making all particles so massive that atoms couldn't form. If the scale were much lower, particles would be too light, and matter wouldn't have the stability needed for complex chemistry. The observed energy scale appears to be fine-tuned for the existence of complex structures like planets, stars, and life. Dr. Steven Weinberg has described this fine-tuning as one of the deepest puzzles in physics. The electroweak scale is approximately 10 times smaller than the Planck scale, where quantum gravity effects become important, a gap so enormous that it's difficult to understand why these scales should be related at all. This hierarchy problem suggests that our understanding of energy scales in fundamental physics remains incomplete. The experimental challenge of reaching Higgs scale energies drove decades of technological innovation in particle accelerator design. Early accelerators from the 1950s and 1960s could probe energy scales up to a few GeV, sufficient to discover particles like the pion and muon. The development of colliding beam technology in the 1970s and 1980s pushed achievable energies into the tens of GeV range, enabling the discovery of the charm and bottom quarks. The construction of the Large Electron-Positron Collider, LEP, at CERN in the 1980s represented a major step toward Higgs scale energies. LEP accelerated electrons and positrons to energies up to 200 GeV, approaching but not quite reaching the energy scale needed for direct Higgs production. LEP's precision measurements of Z boson properties provided indirect evidence that the Higgs boson should have a mass accessible to the next generation of accelerators. Professor Carlo Rubbia, who led the discovery of the W and Z bosons at CERN in 1983, understood that finding these massive particles required not just higher energies, but also more sophisticated detection techniques. The W and Z bosons decay so quickly that they can't be observed directly. Instead, physicists must reconstruct their properties from the particles they decay into. This same approach would prove crucial for Higgs discovery. The energy scale of Higgs production also determines the particle's extremely short lifetime. The Higgs boson exists for only about 10 seconds before decaying into other particles. This lifetime is so brief that even traveling at the speed of light, a Higgs particle would travel only about 10 meters, roughly 1,000th the size of a proton before decaying. The Higgs can never be observed directly. It can only be inferred from statistical analysis of its decay products. Dr. Fabiola Giannetti, who led the ATLAS experiment at the LHC during the Higgs discovery, has described the challenge as Searching for a needle in a haystack when you don't know what the needle looks like, and the haystack is the size of a mountain. The energy scales involved mean that every collision produces dozens of particles, and the Higgs signal must be extracted from this complex background through careful statistical analysis of millions of collision events. The relationship between energy scales and particle discovery also explains why certain predictions of particle physics remain untested. Theories like supersymmetry predict new particles and energy scales beyond even the LHC's reach. Grand unified theories suggest energy scales 10 times higher than current accelerators can achieve. String theory operates at the Planck scale, 10 times beyond current technology. These energy scale gaps represent fundamental limits on what can be tested experimentally with foreseeable technology. The cosmic significance of the electroweak energy scale becomes apparent when we consider stellar evolution and nucleosynthesis. The masses of quarks and leptons, determined by their coupling to the Higgs field, control the rates of nuclear reactions in stellar cores. If these masses were significantly different, stars would burn through their nuclear fuel too quickly or too slowly to provide the billions of years of stable energy output needed for planets to develop complex chemistry and life. Professor Lisa Randall from Harvard University has explored whether the apparent fine-tuning of energy scales might be explained by the existence of extraspatial dimensions. In her models, the weakness of gravity relative to other forces arises because gravitational effects can propagate through additional dimensions while other forces are confined to our familiar three-dimensional space. This could explain why the electroweak scale is so much smaller than the Planck scale. The energy scales relevant to Higgs physics also connect to cosmological observations of dark matter and dark energy. The masses of dark matter particles, if they exist, likely correspond to specific energy scales that determine how these particles interact with ordinary matter. Understanding these energy scales might provide clues to the nature of dark matter and its relationship to the particles and forces we can study directly. Modern particle physics experiments continue to push toward higher energy scales through increasingly sophisticated techniques. Future accelerators like the proposed Future Circular Collider could reach energies 7 to 10 times higher than the LHC, potentially revealing new physics beyond the standard model. Space-based experiments studying cosmic rays can access even higher energy scales, observing particles with energies millions of times beyond any terrestrial accelerator. The discovery of the Higgs boson at the predicted energy scale represents one of the greatest triumphs in the history of experimental physics. It validated not only the theoretical understanding of mass generation, but also the entire framework of quantum field theory and the experimental techniques developed to probe the deepest levels of reality. The energy scale of Higgs discovery marks a milestone in humanity's quest to understand the fundamental structure of existence itself. Chapter 6. Experimental Hunt. The experimental search for the Higgs boson represents one of the most challenging and ambitious scientific endeavors in human history, requiring international collaboration on an unprecedented scale and the development of detector technology sensitive enough to identify fleeting particle signatures among billions of background events. The hunt spanned nearly 3 decades, involved thousands of physicists from dozens of countries, and pushed experimental techniques to their absolute limits in the quest to confirm or refute one of the most important theoretical predictions in physics. The search began in earnest at CERN's Large Electron-Positron Collider, LAP, in the 1990s. LAP was specifically designed to study the properties of the Z boson and search for the Higgs particle through precision measurements of electroweak interactions. The machine accelerated electrons and positrons in opposite directions around a 27-kilometer underground ring, smashing them together at energies up to 200 GeV per beam. These collisions provided the cleanest possible environment for studying fundamental particle interactions. Dr. Rolf Dieter Heuer, who later became CERN's Director General, led efforts to extract maximum sensitivity from LEP's Higgs searches. The experimental approach involved looking for events where a Z boson and Higgs boson were produced together, with the Higgs immediately decaying into a pair of bottom quarks. This signature provided a relatively clean experimental signal, but required enormous statistical precision to distinguish from background processes that could mimic the same final state. LEP's final results, published in 2003, after analyzing data from over 20 million Z boson decays, ruled out the existence of a Higgs boson with mass below 114 GeV, but found tantalizing hints of a possible signal around 115 GeV. The statistical significance wasn't sufficient to claim a discovery, but the data suggested that the Higgs, if it existed, should be found at the lower end of the mass range predicted by theoretical models. The experimental challenge intensified when the search moved to hadron colliders, where protons smash into protons instead of the cleaner electron-positron collisions at LEP. The Tevatron at Fermilab, which began serious Higgs searches in the 2000s, collided protons with antiprotons at energies up to 2 TeV. While this provided enough energy to potentially produce Higgs bosons with masses up to several hundred GeV, the complex nature of proton collisions created enormous experimental challenges. Professor Regina Domina from the University of Rochester, who worked on Higgs searches at the CDF experiment at Fermilab, described the challenge as looking for a whisper in a thunderstorm. Proton collisions produce hundreds of particles in each event, creating a chaotic environment where Higgs decay signatures must be extracted from overwhelming backgrounds. Advanced trigger systems and sophisticated data analysis techniques were required to identify potentially interesting events in real time. The Tevatron experiments developed innovative analysis techniques that would prove crucial for later discoveries. Machine learning algorithms were employed to distinguish signal from background. Statistical methods were refined to extract maximum sensitivity from limited datasets, and systematic uncertainties were carefully controlled to ensure reliable results. Despite heroic efforts, the Tevatron's collision rate and energy were ultimately insufficient to definitively discover or rule out the Higgs boson. The construction of the Large Hadron Collider represented a quantum leap in experimental capability. With a circumference of 27 kilometers and collision energies initially reaching 7 TeV, later upgraded to 13 TeV, the LHC provided both the energy and collision rate needed for decisive Higgs searches. The machine was designed to produce up to 600 million proton-proton collisions per second, creating conditions where Higgs bosons would be produced frequently enough for detailed study. Dr. Fabiola Gianotti led the ATLAS experiment, one of 2 general-purpose detectors built to search for the Higgs at the LHC. ATLAS is a technological marvel weighing 7,000 tons and containing over 100 million electronic channels to record the properties of particles produced in LHC collisions. The detector can measure particle energies, momenta, and trajectories with extraordinary precision, enabling reconstruction of complex collision events. The complementary CMS experiment, led by Dr. Joe Candela during the discovery period, employed different technological approaches to achieve similar scientific goals. CMS features a massive superconducting solenoid magnet that generates magnetic fields 100,000 times stronger than Earth's magnetic field, allowing precise measurement of charged particle momenta. The redundancy provided by having 2 independent experiments was crucial for confirming the Higgs discovery. The experimental signature of Higgs production is extraordinarily subtle. The Higgs boson can be produced through several different mechanisms, most commonly when 2 gluons from colliding protons interact to create a Higgs particle through a quantum mechanical process involving virtual top quark loops. The produced Higgs immediately decays, most often into a pair of bottom quarks, but also into photon pairs, W boson pairs, Z boson pairs, and tau lepton pairs. Professor Albert de Rock from CERN coordinated the theoretical calculations needed to interpret experimental results. These calculations required sophisticated techniques from quantum chromodynamics to predict both Higgs production rates and background processes with sufficient precision to enable discovery. The theoretical uncertainty in Higgs production cross-sections was reduced to the few percent level through years of intensive calculation. The discovery strategy focused on combining multiple decay channels to maximize statistical power. The golden channel involved Higgs decay to 2 photons, which provides a clean experimental signature despite occurring in only about 0.2% of Higgs decays. The 4-lepton channel, where the Higgs decays to 2 Z bosons, which each decay to 2 leptons, provided even cleaner signatures, but with lower rates. The dominant decay to bottom quarks was more challenging due to larger backgrounds. Data analysis required unprecedented statistical sophistication. Dr. Kyle Cranmer from New York University developed advanced statistical frameworks for combining data from multiple channels and experiments. The discovery criteria required demonstrating that the observed data was inconsistent with background-only hypotheses at the 5 sigma level, meaning the probability of observing such a signal by random chance was less than 1 in 3.5 million. The experimental hunt intensified dramatically in 2011 as both ATLAS and CMS began accumulating data at collision energies of 7 TeV. Monthly updates at international conferences showed steady improvement in sensitivity, with both experiments approaching the statistical power needed for discovery. The physics community watched with intense anticipation as exclusion limits tightened and hints of possible signals began to emerge. Dr. Guido Tonelli, spokesperson for CMS during much of the search period, maintained strict protocols to prevent bias in the analysis. The final signal regions were kept blinded until all analysis procedures were finalized, ensuring that knowledge of the results couldn't influence the analysis choices. This level of experimental rigor was essential for maintaining credibility, given the enormous importance of the potential discovery. The breakthrough came in December 2011 when both ATLAS and CMS reported seeing excess events consistent with a Higgs boson around 125 GeV mass. The statistical significance wasn't yet sufficient for discovery, but the concordance between 2 independent experiments strongly suggested that a real signal was emerging. The physics community buzzed with excitement and anticipation for the additional data needed to confirm or refute the tentative signal. The final push toward discovery required analyzing collision data from early 2012 at the increased collision energy of 8 TeV. Both experiments worked around the clock to process and analyze the new data, refining their techniques and reducing systematic uncertainties. The collaboration between experimental teams, computing specialists, and theoretical physicists reached levels of intensity rarely seen in scientific research. Professor Peter Jenny, founding spokesperson of a TLAS, coordinated the preparation for the discovery announcement. The results from both experiments were kept secret until they could be presented simultaneously at CERN. The parallel analysis by independent teams provided crucial confirmation that the observed signals were real rather than experimental artifacts. The discovery announcement on July 4, 2012, represented the culmination of one of the longest and most challenging experimental quests in the history of science. Both ATLAS and CMS reported observing a new particle consistent with the long-sought Higgs boson, with statistical significances exceeding the 5 sigma threshold for discovery. The concordance between independent experiments, the consistency with theoretical predictions, and the decades of careful experimental development all contributed to the profound confidence that humanity had finally detected the particle responsible for giving mass to all matter in the universe. Chapter 7. Discovery Day, July 4, 2012, will forever be remembered as one of the most momentous days in the history of scientific discovery. On this date, In the main auditorium at CERN near Geneva, Switzerland, hundreds of physicists gathered to witness the announcement that would confirm one of the most important theoretical predictions in modern physics. The atmosphere was electric with anticipation as two experimental teams prepared to reveal whether they had finally detected the elusive Higgs boson after nearly half a century of searching. The day began before dawn in the CERN computing centers, where final statistical analyses were being completed under conditions of extraordinary secrecy. Dr. Fabiola Gianotti, spokesperson for the ATLAS experiment, had been working around the clock with her team to finalize their results. Similarly, Dr. Joe Incandela of the CMS experiment was putting finishing touches on the presentation that could change our understanding of the fundamental nature of reality. Both teams had been analyzing collision data in parallel, unaware of each other's specific results until just hours before the announcement. The statistical evidence had been building for months. Throughout the spring of 2012, as the Large Hadron Collider accumulated more collision data at the increased energy of 8 TeV per beam, both ATLAS and CMS had observed growing excesses of events consistent with Higgs boson production and decay. The signal was emerging most clearly in two decay channels: the conversion of Higgs bosons into pairs of photons, and the decay into pairs of Z bosons that subsequently decayed into 4 leptons. Professor Rolf Dieter-Heuer, CERN's Director General, opened the seminar at 9 a.m. Central European Time with remarks about the historic nature of the day. The auditorium was packed beyond capacity, with overflow crowds watching live video feeds in conference rooms throughout CERN. Physicists, who had devoted their careers to the search, sat alongside young graduate students experiencing their first major discovery. The audience included Peter Higgs himself, then 83 years old, who had flown in from Edinburgh to witness the potential confirmation of his 48-year-old theoretical prediction. Dr. Gianotti presented the ATLAS results first, methodically walking through each analysis channel and the sophisticated statistical techniques used to extract signals from background noise. Her presentation revealed that ATLAS had observed a clear excess of events at a mass of approximately 126.5 GeV, with a statistical significance of 5.0 sigma, exactly at the threshold conventionally required to claim a discovery in particle physics. The probability that such a signal could arise by random chance was less than 1 in 3.5 million. The ATLAS analysis had examined several different ways the Higgs boson could decay, combining results from the 2-photon channel, the 4-lepton channel, and other decay modes. Each channel provided independent evidence for the new particle, and the consistency between different decay modes strongly suggested that the observed signal represented a real particle rather than a statistical fluctuation or systematic error. When Dr. Incandela took the stage to present the CMS results, the tension in the auditorium was palpable. The CMS experiment had analyzed the same collision data using independent detectors, analysis techniques, and systematic checks. If both experiments saw similar signals at the same mass, it would provide compelling evidence for discovery. If they disagreed, it might indicate that one or both experiments had made errors in their analysis. CMS had observed an even stronger signal, with a statistical significance of 5.1 sigma at a mass of approximately 125.3 GeV, remarkably close to the ATLAS result. The consistency between two independent experiments using different detector technologies and analysis approaches provided powerful confirmation that both teams were observing the same real physical phenomenon. The particle masses measured by ATLAS and CMS agreed within experimental uncertainties, strongly suggesting they had found the same new particle. The announcement of discovery was delivered with characteristic scientific caution. Both spokespeople carefully explained that they had observed a new particle consistent with the standard model Higgs boson, noting that additional measurements would be needed to confirm that the new particle had all the properties predicted by the Higgs mechanism. However, the assembled physicists understood the magnitude of what they were witnessing, the confirmation of the final missing piece of the standard model of particle physics. Peter Higgs's emotional response became one of the most memorable moments of the day. As the presentations concluded and the strength of the evidence became clear, the elderly physicist was visibly moved to tears. In interviews afterward, Higgs expressed amazement that the theoretical ideas he had developed as a young postdoc had finally been confirmed through experiments of extraordinary technical sophistication. He noted that he never expected the confirmation to come during his lifetime. Professor Francois Englert, Higgs's collaborator who shared the 2013 Nobel Prize for the theoretical prediction, was also present at CERN for the announcement. At 79 years old, Englert had waited even longer than Higgs to see experimental confirmation of their work. The presence of both theoretical pioneers at the discovery announcement provided a direct connection between the original theoretical insights of the 1960s and their experimental confirmation in the 21st century. The discovery represents the culmination of one of the largest collaborative efforts in scientific history. The ATLAS experiment involved over 3,000 physicists from 38 countries, while CMS included more than 4,000 scientists from 42 countries. The analysis of discovery data required processing petabytes of information using advanced computing grids distributed across dozens of institutions worldwide. The scale of international cooperation required to achieve the discovery was unprecedented in the history of experimental physics. Dr. Sergio Bertolucci, CERN's research director during the discovery period, emphasized the technological achievements that made the discovery possible. The Large Hadron Collider had to operate at the cutting edge of accelerator technology, maintaining stable beams of protons traveling at 99.999999991%, the speed of light around the 27-kilometer circumference. The precision required was extraordinary. If the LHC were scaled up to the size of Earth's orbit around the Sun, beam alignment would need to be maintained to within the width of a human hair. The detector technologies that enabled the discovery pushed the boundaries of what was thought possible in experimental physics. The ATLA's detector contains over 100 million electronic channels, each capable of recording precise measurements up to 40 million times per second. The CMS detector features a superconducting magnet that creates magnetic fields 100,000 times stronger than Earth's field while operating at temperatures colder than deep space. The data analysis challenges were equally formidable. The discovery required analyzing billions of collision events to find the few hundred that contained genuine Higgs boson signatures. Advanced machine learning algorithms, sophisticated statistical techniques, and careful control of systematic uncertainties were all essential for extracting the weak Higgs signals from overwhelming backgrounds. The analysis represented a triumph of both computational physics and statistical methodology. News of the discovery spread rapidly around the world, with major media outlets providing live coverage of the CERN seminar. The discovery made front-page headlines in newspapers across the globe and was featured prominently in television news broadcasts. Social media amplified the excitement, with hashtag Higgs Boson trending worldwide as physicists and science enthusiasts shared their excitement about the landmark discovery. The immediate scientific impact was profound. The discovery confirmed the validity of the Higgs mechanism and completed the standard model of particle physics, the theoretical framework that describes all known fundamental particles and 3 of the 4 fundamental forces. It validated decades of theoretical work and provided conclusive evidence for the existence of quantum fields that fill all of space and determine the masses of fundamental particles. Professor John Ellis from King's College London, one of the early pioneers in Higgs phenomenology, described the discovery as the end of a long journey and the beginning of a new adventure. While finding the Higgs boson answered fundamental questions about the origin of mass, it also opened up new avenues for investigation. Detailed study of the Higgs particle's properties could reveal whether our understanding of fundamental physics is complete, or whether new phenomena await discovery at even higher energy scales. The economic and technological implications of the discovery extend far beyond fundamental physics. The technologies developed for the Higgs search, including advanced superconducting magnets, precision detectors, and distributed computing systems, have applications in medical imaging, material science, and information technology. The World Wide Web itself was invented at CERN during earlier particle physics experiments, demonstrating how basic research can lead to transformative technological innovations. July 4, 2012, marked the end of a 48-year quest that began with theoretical insights about the nature of mass and culminated in experimental confirmation, using the most sophisticated scientific instruments ever built. The discovery of the Higgs boson stands as one of humanity's greatest intellectual achievements, revealing fundamental truths about the hidden mechanisms that make existence itself possible. It represents the power of human curiosity, international collaboration, and the relentless pursuit of understanding the deepest mysteries of the natural world. Chapter 8: Particle Portraits. The Higgs boson exists for such a brief moment that it can never be photographed or directly observed. It can only be known through the distinctive signatures it leaves in the sophisticated detectors of particle accelerators. Understanding how physicists see this invisible particle requires appreciating the remarkable detective work involved in reconstructing the properties of something that exists for only 10 seconds and travels less than 10 meters before vanishing into other particles. The portraits we have of the Higgs boson are statistical masterpieces painted from millions of collision events. The challenge of detecting the Higgs boson is comparable to trying to identify a specific person by examining only the debris left after they walk through a house of mirrors, except the person is invisible. The mirrors are quantum fields, and the debris consists of subatomic particles that themselves must be inferred from electronic signals in vast detector arrays. The Higgs boson announces its brief existence only through the precise patterns in which it transforms into other particles. Dr. Fabiola Gianotti has described the detection process as archaeological reconstruction at the quantum level. When a Higgs boson is produced in a collision at the Large Hadron Collider, it immediately begins decaying according to quantum mechanical probabilities. The most common decay pathway, about 58% of the time, involves the Higgs transforming into a bottom quark and bottom antiquark. However, these quarks cannot be observed directly because they are always confined within composite particles called hadrons. The experimental signature of Higgs decay to bottom quarks appears as two jets of hadrons spraying in opposite directions from the collision point. Special algorithms identify these jets as likely containing bottom quarks by looking for secondary vertices points, where the bottom quarks decay after traveling a few millimeters from the primary collision point. The bottom quark's relatively long lifetime, about 1.6 picoseconds, makes it possible to distinguish jets containing bottom quarks from the more common jets produced by lighter quarks. Perhaps the most beautiful experimental signature comes from Higgs decay to two photons, which occurs in only about 0.2% of Higgs decays, but provides an extraordinarily clean signal. When a Higgs boson decays to two photons, these high-energy light particles travel through the detector at the speed of light, leaving characteristic energy deposits in electromagnetic calorimeters. The two photons carry precisely balanced energy and momentum, creating a distinctive signature that can be clearly distinguished from background processes. Professor Maria Spyropoulou from Caltech has pioneered techniques for identifying photon pairs from Higgs decay among the hundreds of photons produced in typical collision events. The key insight is that photons from Higgs decay have a combined energy that precisely equals the Higgs mass times c squared, creating a sharp peak in the invariant mass spectrum when the right photon pairs are identified. This peak emerges from statistical analysis of millions of collision events, gradually becoming visible as more data accumulates. The 4-lepton signature provides perhaps the clearest evidence for Higgs boson properties. In this decay channel, the Higgs transforms into 2 Z bosons, each of which subsequently decays into 2 leptons, electrons, muons, or their antiparticles. The result is 4 charged particles whose combined energy and momentum can be precisely measured, allowing reconstruction of both Z boson masses and the original Higgs mass with extraordinary precision. Dr. Andrei Koratov from the University of Florida led efforts to optimize 4-lepton analysis techniques. The challenge involves identifying genuine 4-lepton events from Higgs decay while rejecting background events that can mimic the same signature. Sophisticated machine learning algorithms analyze dozens of kinematic variables for each event, learning to distinguish subtle differences between signal and background based on the quantum mechanical predictions for how Higgs bosons should decay. The statistical portrait of the Higgs boson emerges through careful combination of multiple decay channels. Each decay mode provides independent information about the particle's properties, and the consistency between different modes provides crucial validation that the observed signals represent a genuine particle rather than experimental artifacts. The combination of channels also improves the overall statistical sensitivity, allowing detection of signals too weak to be seen in any individual decay mode. Modern particle physics detectors function like 3-dimensional cameras capable of recording the positions, energies, and momenta of particles with extraordinary precision. The Atlas detector, for example, can measure the energy of electrons to better than 1% precision and track the paths of charged particles with position accuracy of about 10 micrometers, roughly 1/10 the width of a human hair. These measurements enable reconstruction of particle masses and decay kinematics with sufficient precision to identify rare processes like Higgs production. Professor Tejinder Virdi, one of the founding figures of the CMS detector, emphasized that creating particle portraits requires understanding detector response at the level of individual electronic channels. Modern detectors contain millions of sensing elements, each calibrated to convert particle interactions into digital signals that can be analyzed by computer algorithms. The calibration process involves expositing each detector element to particles of known energy and precisely measuring its response. The time structure of particle detection adds another layer of complexity to creating Higgs portraits. Collision events at the LHC occur every 25 nanoseconds, requiring detector systems that can distinguish signals from different collisions even when they overlap in time. Advanced triggering systems make real-time decisions about which collision events are potentially interesting, recording only about 1 in a million collisions for detailed analysis. Machine learning has revolutionized the creation of particle portraits by enabling pattern recognition in high-dimensional data spaces that exceed human intuition. Dr. Kyle Kramer from New York University has developed neural network architectures that can identify subtle correlations between dozens of measured quantities for each collision event, learning to distinguish Higgs decay signatures from background processes with superhuman accuracy. The statistical techniques used to extract Higgs signals from data involve sophisticated methods for handling systematic uncertainties, sources of experimental error that could bias the results. These include uncertainties in detector calibration, theoretical predictions for background processes, and variations in collision conditions. Advanced statistical frameworks propagate these uncertainties through the entire analysis chain, ensuring that discovery claims are robust against plausible experimental errors. Dr. Ilham Gross from the Weizmann Institute has specialized in developing statistical methods for particle discovery and property measurement. His techniques involve creating mathematical models that describe both signal and background processes, then using maximum likelihood methods to determine which model parameters best describe the observed data. The statistical significance of a potential discovery is quantified using likelihood ratios that compare signal plus background hypotheses to background-only hypotheses. The portrait of the Higgs boson that emerged from the 2012 discovery showed a particle with mass approximately 125 GeV-c², remarkably close to theoretical predictions based on precision electroweak measurements. The particle's production rate agreed well with standard model expectations, and its decay patterns matched theoretical predictions within experimental uncertainties. However, the statistical precision of early measurements left room for the particle to have properties slightly different from the simplest theoretical predictions. Subsequent years of data collection have refined the portrait of the Higgs boson with increasingly precise measurements. The particle's mass is now known to about 0.1%. Precision, 125.25 plus or minus 0.17 GeV-c². Its production rates in different channels have been measured to few percent precision, confirming that the particle couples to other particles in proportion to their masses, exactly as predicted by the Higgs mechanism. Professor Clara Nellist from CERN has led efforts to measure rare Higgs decay modes that provide additional tests of the particle's properties. These include decays to tau lepton pairs, which test the Higgs coupling to the heaviest leptons, and decays to muon pairs, which are predicted to occur only once in every 5,000 Higgs decays. Observing these rare signatures requires analyzing hundreds of millions of collision events to accumulate sufficient statistical samples. The evolving portrait of the Higgs boson continues to reveal new aspects of the particle's behavior. Recent measurements have confirmed that the Higgs couples to itself, a crucial prediction of the theory that the Higgs field is responsible for its own mass. This self-coupling can be studied by looking for events where two Higgs bosons are produced simultaneously, an extremely rare process that requires enormous data samples to observe. Advanced analysis techniques continue to improve the precision of Higgs measurements by extracting more information from existing data. Machine learning algorithms identify subtle correlations that traditional analysis methods miss, while improved theoretical calculations reduce uncertainties in background predictions. The result is an increasingly detailed portrait of a particle that exists for such a brief moment that it challenges our very concepts of observation and measurement. The particle portraits created through decades of experimental development represent one of humanity's greatest achievements in precision measurement and statistical analysis. They reveal not just the properties of a single fundamental particle, but demonstrate our ability to probe the deepest levels of reality through instruments of extraordinary sophistication and international collaborations of unprecedented scale. Chapter 9. Universal Mechanism. The Higgs mechanism operates as a universal mass generation system that affects every fundamental particle in the universe, but does so in ways that reveal profound insights about the nature of physical law and the hidden relationships between seemingly unrelated phenomena. Understanding how this single field can give different masses to different particles while preserving the mathematical elegance of gauge theories opens a window into the deepest principles governing the structure of reality itself. The universality of the Higgs mechanism stems from its operation through what physicists call gauge-invariant interactions. Every fundamental particle that has mass quarks, leptons and the W and Z bosons, acquires that mass by interacting with the same underlying Higgs field that fills all of space. However, the strength of each particle's interaction with the field differs, explaining why particles have such dramatically different masses despite all deriving their mass from the same source. Dr. Steven Weinberg's Nobel Prize-winning insight was recognizing that the Higgs mechanism could simultaneously solve two fundamental problems: explaining why particles have mass and explaining why electromagnetic and weak forces appear so different despite being aspects of the same underlying electroweak force. The mechanism accomplishes this through spontaneous symmetry breaking, where the underlying laws preserve perfect symmetry, but the actual state of the universe appears asymmetric. The mathematical elegance of the universal mechanism lies in how it preserves gauge invariance, the fundamental symmetry that underlies our understanding of forces in nature. Gauge invariance requires that the laws of physics remain unchanged under certain mathematical transformations, but naively adding mass terms to particle equations violates this crucial symmetry. The Higgs mechanism provides mass without breaking gauge invariance by making mass emerge from interactions with a field rather than being an intrinsic property. Professor Gerard T. Hooft's proof that gauge theories with spontaneous symmetry breaking are mathematically consistent or normalizable was crucial for establishing the initiation's validity. Without this proof, physicists couldn't have confidence that theories incorporating the Higgs mechanism would make finite, meaningful predictions. The renormalizability of electroweak theory provided the theoretical foundation for believing that the mechanism represented genuine physics rather than mathematical artifice. The coupling constants that determine how strongly different particles interact with the Higgs field represent some of the most mysterious parameters in physics. These numbers, which range from nearly zero for neutrinos to approximately 1 for the top quark, appear arbitrary from our current understanding, but determine fundamental properties of matter throughout the universe. Why the electron couples to the Higgs field with strength 0.0000024, while the top quark couples with strength near 1, remains one of the deepest unsolved puzzles in physics. The pattern of particle masses reveals tantalizing hints about deeper organizational principles that might govern the universal mechanism. The charged leptons, electron, muon, tau, have mass ratios of approximately 1 to 207 to 3,477, while the up-type quarks show ratios of roughly 1 to 480 to 80,000. These patterns suggest underlying mathematical relationships that our current theories don't explain, but which might point toward more fundamental principles governing the Higgs couplings. Dr. Yohanjiro Nambu's insight about spontaneous symmetry breaking in condensed matter systems provided the conceptual foundation for understanding the universal mechanism. Nambu recognized that the mathematical description of superconductivity, where electrons form Cooper pairs that can flow without resistance, was mathematically analogous to the mechanism needed to give particles mass while preserving gauge invariance in particle physics. The universality of mass generation through the Higgs field creates profound connections between seemingly disparate physical phenomena. The same mechanism that gives mass to quarks and determines the stability of atomic nuclei also affects the properties of neutrinos, influencing how these ghostly particles travel through space and interact with matter. The unity underlying diverse phenomena exemplifies the deep harmony that theoretical physics seeks to uncover. Professor Lisa Randall has explored how the universal mechanism might operate differently in the presence of extra spatial dimensions. In models with additional dimensions, the Higgs field could have different properties in different regions of higher dimensional space, potentially explaining why our three-dimensional slice of spacetime has the particular pattern of particle masses we observe. The mechanism's universality might thus reflect deeper geometric principles operating in spaces we can't directly perceive. The temporal aspects of the universal mechanism raise fascinating questions about cosmic evolution and the possibility of changing physical laws. If the Higgs field could undergo phase transitions, changing its value throughout space, then particle masses would change accordingly, fundamentally altering the nature of matter and the possibilities for complex structure formation. Some theoretical models suggest that such phase transitions might have occurred in the early universe or could occur in the far future. Modern precision measurements of Higgs boson properties provide increasingly detailed tests of the mechanism's universality. The Standard Model predicts specific relationships between the Higgs coupling strengths to different particles. An experimental verification of these predictions tests whether the observed particle is indeed responsible for the universal mass generation mechanism. Any deviations from predicted coupling patterns could indicate new physics beyond our current understanding. The mechanism's universality extends to its role in determining the fundamental constants that govern atomic and nuclear physics. The masses of quarks, determined by their Higgs couplings, control the binding energies of atomic nuclei and the rates of nuclear reactions in stellar cores. The electron mass, similarly determined, affects atomic structure, chemical bonding, and the stability of matter. The Higgs mechanism thus shapes every level of physical structure from subatomic to cosmic scales. Dr. Frank Wilczek has investigated how the universal mechanism might be connected to the strong force through quantum corrections involving the top quark. The top quark's enormous mass, nearly 200 times heavier than the proton, creates large quantum mechanical effects that could influence the properties of the Higgs field itself. These quantum corrections might provide clues about physics beyond the Standard Model or hint at deeper unified theories. The universality of the Higgs mechanism also raises profound questions about the relationship between mass and information. If mass emerges from interactions with quantum fields rather than being intrinsic to particles, then mass represents a form of relational property that depends on the information content of field configurations. This suggests deep connections between mass, energy, and information that might point toward more fundamental descriptions of physical reality. Professor Edward Witten's work on string theory suggests that the universal mechanism might represent the low-energy manifestation of more fundamental processes involving the geometry of higher dimensional spaces. In string theory, particle masses and coupling constants emerge from the specific ways that extra dimensions are compactified, potentially providing a geometric explanation for the seemingly arbitrary parameters that characterize the Higgs mechanism. The search for additional Higgs bosons represents one of the most active areas in contemporary particle physics research. Many theoretical extensions of the Standard Model predict the existence of multiple Higgs fields with different properties and coupling patterns. Discovering such additional fields would reveal whether the universal mechanism we observe represents the complete picture or merely the tip of a larger iceberg of mass generation phenomena. The universal mechanism's influence on cosmological evolution provides another window into its fundamental nature. The Higgs field's properties affect the expansion rate of the universe, the formation of cosmic structure, and the possibility of phase transitions that could dramatically alter physical laws. Understanding these cosmological connections might reveal whether our universe's particular realization of the Higgs mechanism is unique or represents one possibility among many. Recent theoretical investigations have explored whether the universal mechanism might emerge from even more fundamental principles involving quantum gravity, holographic duality, or emergent spacetime. These approaches suggest that mass generation might be an emergent property of deeper geometric or informational structures rather than a fundamental aspect of physical law. Such perspectives could revolutionize our understanding of the relationship between matter, energy, and spacetime. The universality of the Higgs mechanism ultimately reveals that mass, our most familiar physical property, emerges from one of the most subtle and sophisticated mechanisms in fundamental physics. The same field that gives weight to a grain of sand operates through quantum mechanical interactions that required the most advanced theoretical insights and experimental techniques in human history to understand. This mechanism represents both the culmination of 20th century physics and the foundation for 21st century investigations into the deeper principles governing existence itself. Chapter 10: Reality's Foundation. The discovery and understanding of the Higgs mechanism has revealed that what we consider the most solid, tangible aspects of reality, the mass and inertia of matter itself, emerge from invisible quantum processes operating at the deepest levels of existence. This realization forces us to fundamentally reconsider the nature of physical reality, suggesting that everything we can touch, see, and measure represents surface manifestations of far more subtle and complex underlying phenomena that remain largely hidden from direct experience. The philosophical implications begin with recognizing that mass is not a fundamental property of matter, but rather an acquired characteristic that particles gain through interaction with quantum fields. This insight suggests that many other properties we consider basic or fundamental might also be emergent rather than intrinsic. The solidity of matter, the stability of atoms, the strength of chemical bonds, all of these familiar aspects of reality depend ultimately on the invisible activity of quantum fields that fill every cubic centimeter of space. Dr. David Bohm's concept of implicate order finds remarkable validation in the Higgs mechanism, which shows that the manifest properties of matter emerge from hidden relationships within an underlying quantum field structure. According to Bohm's framework, what we observe as separate particles and distinct properties represent explicate order surface manifestations of deeper, interconnected processes that operate according to principles we're only beginning to understand. The Higgs field reveals that empty space itself possesses structure and properties that actively shape the behavior of matter and energy. This challenges the classical notion of space as a passive container for physical events and suggests instead that space is a dynamic participant in physical processes. The vacuum isn't empty, but filled with invisible fields whose fluctuations and interactions determine the fundamental characteristics of everything we observe. Professor John Wheeler's vision of physics as emerging from information finds resonance in the Higgs mechanism's dependence on field configurations that can be understood as distributed information patterns. The mass of a particle represents information about its coupling strength to the Higgs field, while the field's vacuum expectation value encodes information about the fundamental energy scale of electroweak interactions. Reality appears to be built from information as much as from matter and energy. The mechanism also illuminates the relationship between symmetry and reality in ways that challenge our intuitive understanding of both concepts. The underlying laws of physics possess perfect symmetries that are hidden or broken by the actual state of the universe, creating the appearance of asymmetric phenomena from symmetric principles. This suggests that reality operates on multiple levels: the level of underlying law and the level of manifest phenomena, with complex relationships between these levels. Dr. Murray Gell-Mann's concept of the quark and the jaguar, the relationship between fundamental physics and emergent complexity, gains new depth from understanding the Higgs mechanism. The mass of quarks, determined by their interaction with the Higgs field, influences nuclear binding energies, which affect stellar evolution, which shapes planetary formation, which influences biological evolution. The Higgs mechanism thus connects the deepest level of fundamental physics to the emergence of complexity and life. The universality of the Higgs mechanism raises profound questions about the relationship between physical law and cosmic structure. Why does the universe contain a field with the specific properties needed to generate the particular pattern of particle masses we observe? The apparent fine-tuning of the Higgs field's properties for the existence of complex structure suggests either extraordinary cosmic coincidence or deeper organizing principles that we haven't yet discovered. Professor Frank Wilczek has explored how the Higgs mechanism might represent just one example of a more general principle or complex. Phenomena emerge from the interplay between symmetry and symmetry breaking. This symmetry-complexity relationship might govern not only fundamental particle physics, but also the emergence of structure at every level of organization, from atomic to biological to cosmic scales. The temporal aspects of reality's foundation become apparent when we consider that the Higgs field has been actively generating mass for every particle throughout the 13.8 billion year history of the universe. Every star that ever formed, every planet that ever coalesced, every living creature that ever evolved, all exist because the Higgs field has continuously maintained the mass relationships that make complex structure formation possible. This raises the remarkable possibility that reality's foundation is not static but represents an ongoing, dynamic process. The Higgs field doesn't just determine particle masses once and for all. It continuously regenerates these properties through quantum interactions that occur trillions of times per second throughout every cubic centimeter of space. Mass is not a property that particles have, but rather something they continuously acquire through participation in quantum field processes. The implications extend to our understanding of identity and persistence over time. If the mass that defines the properties of your atoms is continuously being generated through quantum field interactions, in what sense do you remain the same person from moment to moment? The Higgs mechanism suggests that identity itself might be a process rather than a state, a pattern of relationships maintained through continuous interaction with underlying quantum processes. Dr. Lee Smolin's exploration of time reborn gains new relevance from the Higgs mechanism's role in cosmic evolution. If physical laws can emerge from quantum processes rather than being eternal and unchanging, then the Higgs mechanism might represent just one phase in a larger cosmic evolution of physical law itself. The particular mass generation mechanism we observe might have emerged from earlier, more fundamental processes and can eventually evolve into something different. The relationship between consciousness and physical reality takes on new dimensions when we recognize that conscious experience depends on neural processes that depend on biochemical processes that depend on atomic structure that depends on particle masses generated by the Higgs mechanism. Consciousness thus emerges from a vast hierarchy of increasingly fundamental levels, ultimately grounded in quantum field processes that operate far below the threshold of direct awareness. Professor Roger Penrose's investigation of quantum effects in consciousness gains additional depth from understanding that the masses of particles involved in neural processes are themselves quantum mechanical phenomena. If consciousness does indeed depend on quantum processes in the brain, then the Higgs mechanism provides the foundation for the possibility of consciousness by enabling the existence of the massive particles needed for complex biological systems. The discovery of the Higgs mechanism also reveals the extraordinary power of human reason to penetrate beyond surface appearances and discover hidden aspects of reality. The theoretical prediction of the mechanism required mathematical insights that went far beyond anything accessible through direct experience, while experimental confirmation required technological achievements that pushed human capabilities to their limits. This demonstrates that consciousness possesses capabilities for understanding reality that extend far beyond the evolutionary pressures that presumably shaped its development. The mechanism's universality suggests that physical reality operates according to unified principles that connect phenomena across all scales of space and time. The same quantum field dynamics that determine the mass of an electron also influence the evolution of galaxies through their effects on stellar nucleosynthesis and cosmic structure formation. Reality appears to be fundamentally interconnected rather than composed of separate, independent components. Modern investigations in the quantum entanglement and non-locality find new context in the Higgs mechanism's demonstration that local properties, like particle mass, can emerge from non-local field configurations. The mass of a particle represents information about its coupling to a field that exists everywhere in space, suggesting that local and non-local aspects of reality are more intimately connected than classical physics assumed. The search for physics beyond the standard model, including dark matter, dark energy, and quantum gravity, gains new urgency from recognizing that the Higgs mechanism despite its explanatory power, leaves many fundamental questions unanswered. Why does the Higgs field have its particular properties? Are there additional fields that shape reality in ways we haven't yet discovered? What determines the values of the coupling constants that characterize particle interactions with the Higgs field? These questions point toward even deeper levels of reality's foundation that remain hidden from current understanding. The Higgs mechanism reveals that reality has invisible layers of extraordinary sophistication and beauty, but it also suggests that these layers might extend indefinitely deeper, offering endless opportunities for discovery and wonder about the fundamental nature of existence. The ultimate lesson of the Higgs mechanism might be that reality is far more subtle, interconnected, and mysterious than our everyday experience suggests, while simultaneously being comprehensible through human reason and technological capability. We live in a universe where invisible quantum processes continuously generate the most basic properties of matter. Yet we can discover and understand these processes through the remarkable capacities of consciousness applied to the pursuit of knowledge about the deepest foundations of existence itself. Chapter 11. Future Mysteries. The discovery of the Higgs boson, far from closing the book on fundamental physics, has opened doorways to mysteries that may be even more profound than the questions it answered. As physicists probe deeper into the properties of this remarkable particle and the mechanism it represents, they uncover puzzles that hint at entirely new layers of reality waiting to be discovered. The Higgs boson represents not an ending, but a beginning, the first glimpse into aspects of nature that could revolutionize our understanding of existence itself. One of the most intriguing mysteries centers around the precise value of the Higgs boson's mass, 125.25 GeV per c squared. This number appears to place our universe in an extraordinary position between stability and instability. Theoretical calculations suggest that if the Higgs mass were just a few GeV higher, our universe would be completely stable for eternity. If it were a few GeV lower, vacuum decay would be inevitable, eventually destroying all matter and energy. Instead, we appear to live in a metastable universe, balanced precariously on the edge between these extremes. Dr. Joseph Liken from Fermilab has calculated that our universe's current configuration might be stable for periods much longer than its current age, but could eventually undergo a catastrophic phase transition that would propagate at the speed of light, transforming the fundamental properties of matter throughout cosmic space. This possibility raises profound questions. Did the Higgs field acquire its current value through random cosmic processes? Or do unknown principles determine the apparent fine-tuning we observe? The hierarchy problem represents another fundamental mystery that the Higgs discovery has made more acute rather than resolving. Quantum corrections to the Higgs mass from virtual particles should drive its mass to enormous values, close to the Planck scale, where quantum gravity effects become important. The fact that the Higgs has a relatively modest mass requires extraordinarily precise cancellation between different quantum contributions, a level of fine-tuning that seems almost impossible to achieve through natural processes. Professor Nima Arkanihand from the Institute for Advanced Study has explored whether solutions to the hierarchy problem might require entirely new physical principles or additional dimensions of space that remain hidden from direct observation. Supersymmetry, extra dimensions, and composite Higgs models all represent attempts to explain the hierarchy problem, but each makes additional predictions that haven't yet been confirmed experimentally. The mystery deepens as increasingly sophisticated searches fail to find evidence for these proposed solutions. The search for additional Higgs bosons represents one of the most active frontiers in contemporary particle physics. Many theoretical models predict that the particle discovered in 2012 is just one member of a larger family of Higgs-like particles with different properties and masses. These additional fields might be responsible for dark matter, the matter-antimatter asymmetry of the universe, or other unexplained cosmic phenomena. Dr. John Ellis has outlined experimental strategies for discovering additional Higgs particles through their subtle effects on the properties of the known Higgs boson. Virtual particles associated with new Higgs fields would create quantum corrections that slightly modify how the discovered Higgs particle decays and interacts. Detecting these minute effects requires unprecedented precision in measuring Higgs properties, pushing experimental techniques to their absolute limits. The relationship between the Higgs mechanism and dark matter remains one of the most tantalizing unsolved puzzles in physics. Dark matter comprises roughly 85% of all matter in the universe, yet we have no confirmed understanding of what it consists of or how it interacts with ordinary matter. Some theoretical models suggest that dark matter particles might acquire their masses through interaction with additional Higgs fields, creating hidden sectors of physics that operate parallel to, but largely separate from the standard model. Professor Catherine Fries from the University of Michigan has explored scenarios where dark matter particles interact with Higgs fields in ways that could be detected through their effects on cosmic structure formation or through direct detection experiments deep underground. The discovery of such interactions would represent the first connection between the Higgs mechanism and the cosmic dark sector, potentially opening entirely new avenues for understanding the universe's hidden matter content. The cosmological implications of the Higgs mechanism extend far beyond current experimental reach but raise fundamental questions about the nature of cosmic evolution. If the Higgs field underwent a phase transition in the early universe, switching from zero to its current non-zero value, this transition might have influenced cosmic inflation, the generation of matter-antimatter asymmetry, and the formation of cosmic structure on the largest scales. Dr. Alan Guth's investigations of cosmic inflation suggest that Higgs field dynamics during the universe's first fraction of a second might have played a crucial role in creating the density fluctuations that eventually grew into galaxies, clusters, and cosmic voids. Understanding these connections requires theoretical frameworks that combine particle physics with cosmology in ways that challenge the boundaries between traditionally separate fields of study. The possibility of Higgs field variations across cosmic space and time raises extraordinary questions about whether the fundamental laws of physics are truly constant. If the Higgs field could have different values in different regions of space, either within our observable universe or in parallel universe domains, then particle masses and the fundamental constants of nature might vary with location and cosmic epoch. Professor Max Tegmark's investigation of the multiverse hypothesis suggests that the particular value of the Higgs field in our cosmic region might reflect anthropic selection. We observe this value because only universes with these properties can support the complex chemistry needed for life and consciousness. This possibility connects the deepest questions in fundamental physics to the ultimate question of why our universe appears fine-tuned for existence. The search for connections between the Higgs mechanism and quantum gravity represents perhaps the most ambitious frontier in theoretical physics. String theory, loop quantum gravity, and other approaches to quantum gravity all make predictions about how the Higgs field might behave in extreme gravitational environments or how gravity itself might emerge from deeper quantum field processes. Dr. Edward Witten's work on string theory suggests that the Higgs field might represent the low-energy manifestation of geometric processes in higher dimensional spaces we can't directly perceive. In these models, particle masses and coupling constants emerge from the specific ways that extra dimensions are compactified, potentially providing a geometric explanation for the apparently arbitrary parameters that characterize the Higgs mechanism. The technological frontiers needed to explore these mysteries require unprecedented advances in experimental capability. Future particle accelerators, like the proposed Future Circular Collider, could reach energies 10 times higher than the LHC, potentially revealing new particles and interactions that remain hidden at current energy scales. Space-based detectors might observe cosmic phenomena that provide information about Higgs field behavior in extreme astrophysical environments. Professor Maria Spirapoulou has outlined how quantum technologies, including quantum sensors, quantum computers, and quantum communication systems might provide new approaches to studying fundamental physics. Quantum sensors could detect minute variations in fundamental constants that might reveal Higgs field fluctuations, while quantum computers could simulate complex field theories that remain beyond the reach of classical computational methods. The implications for consciousness and the nature of mind represent another frontier where Higgs physics intersects with the deepest mysteries of existence. If consciousness depends on quantum processes that involve particle masses generated by the Higgs mechanism, then understanding this mechanism might provide insights into the relationship between mind and matter that have eluded philosophical investigation for centuries. Dr. Roger Penrose's exploration of quantum effects in consciousness takes on new dimensions when we recognize that the masses of particles involved in neural processes are themselves quantum mechanical phenomena generated by field interactions. The possibility that consciousness might depend on subtle quantum field effects opens speculative but tantalizing connections between fundamental physics and the nature of subjective experience. The search for patterns in particle masses and coupling constants continues to reveal hints of deeper organizational principles that our current theories don't explain. The ratios between quark masses, the relationship between lepton masses, and the numerical values of fundamental coupling constants all suggest underlying mathematical relationships that might point toward more fundamental descriptions of physical law. Professor Frank Wilczek's investigation of anyonic quantum systems and topological quantum computing suggests that the Higgs mechanism might be connected to exotic quantum phenomena that could revolutionize both our understanding of fundamental physics and our technological capabilities. These connections between abstract theoretical physics and practical quantum technologies demonstrate how the deepest mysteries often lead to the most transformative applications. As we stand at the threshold of new discoveries that might emerge from studying the Higgs mechanism in greater detail, we confront questions that extend to the very foundations of existence. Are there limits to how deeply we can understand physical reality? Do the patterns we observe in particle physics reflect mathematical necessities or cosmic contingencies? What does the extraordinary fine-tuning apparent in the Higgs mechanism tell us about the nature of physical law and our place in cosmic evolution? The future mysteries surrounding the Higgs boson remind us that each major discovery in fundamental physics reveals new horizons of questions rather than providing final answers. The mechanism that explains why particles have mass opens doorways to understanding dark matter, cosmic evolution, quantum gravity, and perhaps even consciousness itself. In pursuing these mysteries, we continue humanity's greatest adventure, the quest to understand the deepest nature of the reality we inhabit and our relationship to the cosmic processes that make existence possible. Throughout this extraordinary journey into the discovery and implications of the Higgs boson, we have uncovered revelations that fundamentally transform our understanding of reality itself. We explored how the most basic property we experience, the mass of matter, emerges not from the intrinsic nature of particles, but from their interactions with an invisible field that fills every cubic centimeter of space throughout the entire universe. We witnessed how this single mechanism solves one of the deepest puzzles in theoretical physics while revealing hidden layers of reality that operate far beyond our direct perception. We discovered how the search for this elusive particle required building the most sophisticated scientific instruments in human history and developing experimental techniques capable of detecting signals so subtle they emerge only through statistical analysis of billions of collision events. The discovery represents not just the triumph of theoretical insight, but a demonstration of humanity's extraordinary capacity to probe the deepest levels of existence through international collaboration, technological innovation, and sheer intellectual persistence. But perhaps the most profound revelation is how the Higgs mechanism illuminates the relationship between the visible and invisible aspects of reality. We live immersed in quantum fields that continuously generate the mass, stability, and structure of every atom in our bodies. Yet these fields remain completely hidden from our direct experience. The familiar world of solid objects and predictable physics emerges from quantum foundations that are far stranger and more wonderful than our everyday experience suggests. As you continue through your daily life after experiencing this cosmic perspective, remember that every breath you take, every step you walk, every thought you think depends on quantum processes that operate at scales far below anything you can directly perceive. The electrons flowing through your nervous system, the protons and neutrons forming the nuclei of your atoms, the quarks that make up those nuclear particles, all of them owe their masses to continuous interaction with the invisible Higgs field that permeates all of space. When you hold an object in your hand and feel its weight, you are experiencing the manifestation of quantum field interactions that occur trillions of times per second throughout every cubic millimeter of the object's volume. The solidity you feel isn't an intrinsic property of matter, but an emergent phenomenon arising from the extraordinary complexity of quantum processes that remain completely hidden from direct observation. You are not separate from these fundamental processes. You are these processes organized in ways complex enough to generate consciousness, wonder, and the capacity to understand the very mechanisms that make your existence possible. Your ability to contemplate the Higgs mechanism represents one of the universe's most remarkable achievements. Matter organized in such sophisticated ways that it can discover and comprehend the invisible fields that determine its own fundamental properties. The Higgs field reveals that the universe operates according to principles of extraordinary elegance and unity. The same mechanism that gives mass to the smallest subatomic particles also determines the nuclear binding energies that power stars, the chemical properties that enable biological complexity, and the gravitational dynamics that shape cosmic structure on the largest scales. Reality emerges from unified quantum processes that connect every level of organization from the microscopic to the cosmic. The discovery also reminds us that our most successful scientific theories often reveal reality to be far stranger than our ordinary experience suggests. The Higgs mechanism shows that mass, our most familiar physical property, actually emerges from interactions with quantum fields that exist everywhere yet remain invisible, that participate in spontaneous symmetry-breaking processes that hide the underlying unity of fundamental forces, and that continuously regenerate the properties of matter through quantum interactions that occur at unimaginably rapid rates. This strangeness isn't a limitation of our understanding, but rather a revelation of the extraordinary sophistication and beauty underlying physical reality. The universe is not just more complex than we imagine, it's more elegant, more unified, and more mysterious than we could have conceived before developing the wide and the theoretical and experimental tools needed to probe its deepest levels. The Higgs discovery also demonstrates the remarkable power of human reason to extend far beyond the evolutionary pressures that shaped its development. The theoretical prediction of the Higgs mechanism required mathematical insights that went completely beyond anything accessible through direct experience, while experimental confirmation required technological capabilities that pushed human achievement to its absolute limits. Our capacity to understand reality appears to transcend the practical purposes for which consciousness presumably evolved. Yet the discovery simultaneously reveals how much we still don't understand. The hierarchy problem, the apparent fine-tuning of the Higgs mass, the possible existence of additional Higgs fields, and the connections to dark matter and cosmic evolution all point toward deeper mysteries that might require entirely new theoretical frameworks to comprehend. Each answer we discover reveals new questions that extend ever further into the unknown. The precision required for the discovery, identifying a single type of particle among billions of collision events, measuring its properties to fractions of a percent accuracy, and confirming theoretical predictions made decades before the technology existed to test them, demonstrates both the extraordinary sophistication of modern science and the deep mathematical harmony underlying physical law. The universe appears to operate according to principles accessible to human reason, even when those principles involve phenomena far beyond direct experience.